Hello everyone. In our last class, we studied about the normal shift. What was normal shift? It was, suppose this is the position up to which the liquid is filled in this system and we have an object here. So the position of what? Its image or the apparent position of the object which is seen by the observer and hence the height up to which this object appears to be raised up is called the normal shift, right? What happened here exactly? We are talking about the ray which is going straight along the normal, which do not bend, right? It bends. It's not like that it doesn't bend, it bends, but it bends in the same plane. For example, this light ray is either coming out of the plane or going inside the plane, so you won't find the bending phenomena which is appearing at some angle, right? But the other ray which is going in this direction, if this is normal, instead of going straight like this, it will bend away from the normal because right now the ray is traveling from denser to rarer medium. So if I extend this ray in this direction, where will I get at the cross section of these two rays which are extended backwards? Here is the apparent position of this object. So this height up to which the object appears to be raised up is called the normal shift. Where do we see this phenomena? We see this phenomena at what? Swimming pools, bucket, even the glass tumbler, the glass full of water. If you watch the base of the water by looking directly into the glass like this, suppose this is a glass, I am looking directly above it, so you will find the base appearing to be a bit raised up. Same thing happens in case of bucket full of water and then swimming pools, the base is raised up due to this phenomena, that is refraction. Now we are moving on in the same trend. See, I have an arrangement where the water level or the denser medium is filled up to this point, alright, and I have an object here. So I'll first again talk about this ray which is going straight along the normal and this ray which is going at some angle, and hence this angle, the refracted ray, this is the incident ray on this interface. This is the incident ray, that means this is the angle of incidence, and the refracted ray will not be in this direction, it will be what? It will be in this direction because the ray is traveling from denser to rarer, it bends away from the normal. Now what happens if I increase the angle of incidence? For example, let us say this is I1 and my ray is going at larger angle of incidence, for example this. Now here I2 is definitely greater than I1, so that will make the refraction more prominent and the ray is going to bend more away from the normal, right? So consequently, for example, if the ray was somewhere here, so the bending was not that prominent. So you can see the nature of bending in these three rays. The bending is getting more and more prominent, so that's what will happen after a while. The refracted ray at a stage will come, the refracted ray will go exactly along the interface, along this surface where the this interface is present, and that particular angle is called critical angle, where bending is so much that the refracted ray appears to go along the interface. This is what happens, and this angle is called critical angle. So today we are going to talk about this critical angle, and if I have another angle, another ray which is even further greater than this critical angle, what will happen? The ray which is incident on the interface at an angle which is greater than critical angle, then this ray will not go outside because all the limits of bending away from the normal has been already crossed. At this point the refracted ray was going along the surface, so there is no scope of any further bending, right? So if you follow the same loop, the ray is bending more, bending further more, and here going along it is bending so much that it is going along the surface, so that means further bending will send the ray back in the medium, right? So what will happen? This particular ray will reflect back in the medium. This is what happens if the angle of incidence is greater than critical angle, then the ray gets reflected back in the medium, and this whole phenomena is known as total internal reflection. This whole phenomena is known as total internal reflection. Alright. So I will just explain you the definition of what is total internal reflection. The phenomena of, mark my words, the phenomena of reflection of light ray in the denser medium, because light was traveling from where? From denser to rarer, right? So the phenomena of reflection of light in the denser medium from the interface when the ray traveling in the denser medium towards interface is incident on the interface at an angle which is greater than critical angle. I'll repeat again in short. It is the phenomena of reflection of light in the denser medium when the ray traveling in denser medium is incident at an angle greater than critical angle on the interface. Alright, it's a bit shorted. Now, what exactly happened at TIR? I'll now show you only the critical angle thing and the total internal reflection thing. See, guys, have you been following my lectures, the projector lectures, where I'm showing you videos and images of all the different things, right? Do follow those as well, because that will, if you are unable to get this thing at this point, that projected images, the real images of any phenomena or apparatus will give you more clarity. Alright, so don't miss those lectures. I'm showing you, okay, I'll show you two things. One is, first of all, I'm marking my object here. I'm taking the incident ray which is incident at critical angle. So what will happen? This ray, if it is incident at critical angle, what will happen? The refracted ray will go along the normal, right? Along the surface, sorry, not the normal, along the surface. So this angle, which is actually the angle of refraction, it is what? 90 degree, right? So at critical angle, you can write it, at critical angle, what happens? According to Snell's law, okay, now Snell's law is in the picture, so you are again going to use mu1 and mu2 thing. This is the denser medium mu2, this is the rarer medium mu1. So what are two necessary conditions which are definitely required for TIR to happen? Before I move on to this derivation part, what do you think the two necessary conditions are? Number one, the ray must be traveling from what? Denser to rarer medium. If the ray is traveling from rarer to denser medium, there is going to be a refraction, alright, which you have done in prisms and glass slabs. But if ray is traveling from denser to rarer, so the refracted ray tends to shift away from the normal, and in that process there comes a point where it goes exactly along the surface, which is called critical angle. So the first necessary condition is, I would write necessary conditions. First is the ray must be traveling from denser towards rarer medium, and second is TIR, that is total internal reflection, do not take place at every angle. It takes only at those angles which are greater than critical angle. So second necessary condition become that angle is greater than critical angle. Which angle is greater than? This is the the angle of incidence, right? Okay. So according to Snell's law, what is Snell's law? Sin I over sin R is equal to what? 1 mu2 or 2 mu1. I have repeated this thing so many times, now you guys actually know. For the last time, the ray is traveling from mu2 to mu1. So I would write mu from 2 to 1, and this thing is converted into mu1 to mu2. Alright. So sin I upon sin I is equal to mu upon mu2. What if I asked you the diffractive index of this denser medium is? What is refractive index? It would be the refractive index of medium upon refractive index of the surrounding. So this is basically 1 upon mu. Take this and this part. Sin I upon sin R is 1 upon mu. That means put values I equal to critical angle, sin IC over sin R. What is R? R is equal to 90 degree. Sin 90 is equal to 1 upon mu. That means sin IC is equal to 1 upon mu. this is a condition, this is a relation which explains you fact that the critical angle is inversely proportional to refractive index. And this is that important property on which we are going to study about a lot of practical applications which are used in total internal reflection.